In an SN1 reaction, the overall rate is controlled by the rate of the slowest step. So it can't be any faster than the slowest part of the reaction. So the rate here is dependent only on the concentration of the substrate or alkyl halide. And so these reactions, because they only depend on the substrate, are going to be unimolecular. So substitution is the S, the N part is nucleophilic, and the 1 is unimolecular. The first step of these reactions is to form a carbocation. And if the reaction can't form a carbocation, it's not going to happen. So if we have our cats again, that bed is the alkyl halide. The cat here, the gray one, is the leaving group. And here's my nucleophile cat. So in an SN1 reaction, instead of being attacked by the orange cat, the leaving group just decides on its own to leave. That's just leaving the substrate, which will leave behind the empty bed. So the empty bed is the carbocation, because it's missing a cat. And at that point, the nucleophile can enter into the bed and then form a new product. The reactivity of these is actually the opposite of the SN2 reaction, and the rate here depends on the ability to form a stable carbocation. So our most stable carbocation is going to have the strongest support group, or the most groups around where the leaving group is. So on here, the Br is the leaving group. I have this one carbon that's supported by 3 carbon groups. So this is a tertiary alkyl halide that will form a tertiary carbocation. So this is the carbocation that would form. If I have 2 groups here, this is a secondary, which would form this carbocation. Here's a primary that would form a carbocation here. And then for the CH3, I would just have a CH3 carbocation. This is a methyl. So if I want to stabilize a carbocation, I want more friends around. The best one at stabilizing is the tertiary. This reaction rate here is 1.2 million, whereas it drops off very greatly here to 12 with the secondary, and the reaction rate for a primary is 1, and then it's less than 1 for the methyl. So these are the carbocations that are formed in that process. We have methyl, the primary, secondary, tertiary, and then the one that is just a little bit more stable than the tertiary is the allylic carbocation. So that's the carbon next to the double bond. This is stabilized through resonance. And the benzylic is also resonance stabilized. In the mechanism of the SN1 reaction, the stereochemistry that results from an SN1 reaction is actually a mixture. Because we form the carbocation, here is our empty orbital, so there's no groups here. Once we form this carbocation after the leaving group has left, this is a planar molecule. The nucleophile can attack from either side. So just like before, the best leaving groups are the ones that can stabilize their own negative charge. We can see the leaving group reactivity here. So water is the best leaving group because it doesn't even have an anion to stable. It's just stable by itself. Then we have this OTS again, and then we can see the trends that we saw previously. For a SN1 reaction, we can use any nucleophile because once we form the carbocation, we just need a nucleophile present. So you can see the different ones here. They can be neutral like water, or you can use negative ones, different halogens or methoxide, cyanide, etc. The solvents that we want to use for SN1 reactions are polar protic because they support the cation. So these electron lone pairs around here can support the carbocation that is formed. If we did this particular reaction with ethanol and some alcohol, water is going to be the speediest reaction followed by a mixture. And then ethanol by itself, which doesn't donate protons very easily, is 1. So in this reaction, if we look at what's going to form, we have a tertiary alkyl halide. So that's going to be a good substrate for this reaction because it's tertiary, it can stabilize a positive charge. My leaving group is here. So the first step here is for the leaving group to leave. So we have loss of leaving group. So these electrons between the carbon and the Br are going to break. And once those electrons have left, I have a positive charge, and then I have a Br minus here. So I form this tertiary carbocation, which is stable. Water is now my nucleophile. So the lone pairs from here can now attack or hug the empty space. And all of the things come along. So I have this O with this positive charge here on the oxygen. Oxygen does not want to be positively charged, so we'll have a proton transfer. So if you want to, you can think about the bromine picking up that extra hydrogen. And then we end up with the OH group here. So a tertiary alkyl halide, and we get a tertiary alcohol in the process. So let's look at a couple of problems here. I have a benzylic substrate. So that's going to be very good at stabilizing carbocation. I have the chlorine leaving group. The OCH3 is my nucleophile. And because we're doing SN1 reactions, because it's benzylic, my product will have no stereochemistry. This will just show a mixture. All right, here is a tertiary alkyl halide. The Br is going to get swapped out with my nucleophile. So I'm going to get left with an alcohol. So we've seen the substitution reaction. Now we're going to look at the elimination reaction, which will give us an alkene. So elimination is the opposite of addition. So instead of adding a group, we're going to take one away and create an alkene. And sometimes this can compete with substitution reactions, especially for SN1 reactions. So in Zaitsev rules for elimination reaction, the more substituted alkene is going to form. So in elimination reactions, we're dealing with bases instead of nucleophiles. And the alcohol below here is the solvent that we're going to do it in. So that's not really involved in our reaction, it's just what the compound is stirring in. The base is going to take the proton that is next door to the leaving group. So here's my leaving group. Base will abstract H next door to leaving group. So on this particular compound, this 2-bromobutane, I have H, I'll call this one A, and I'm going to call this one B. So if my base plucks HA, the electrons from the H to the carbon are going to come here to form a double bond, kicking off the leaving group. So my double bond will form right there, and my Br is gone. So this is from HA, and this is a monosubstituted alkene because it has one group coming off of the double bond. Now, if I take the base and abstract HB, these electrons come here, my Br leaves. My double bond will form here. This is disubstituted. So I have two groups coming off of that alkene. This, according to Zaitsev's rule, is the major product. Because the more substituted alkene will form as the major product. This actually occurs in 81% yield versus 19% here. So if we do this reaction again with the next one, I have possibilities of protons here. There's HA, because we're looking at the H next to the Br, and this one is also HA. So I don't have to worry about that one as part of the reaction. And then I have here an HB. So if I take HA, my double bond will form here. I get a disubstituted alkene. This is from HA. There's my carbon skeleton. And taking HB is going to give me the double bond right there. This is now tri-substituted. It's HB. This is my major. This is 70%. This is 30%. The driving force for an elimination reaction is the base. So these in the box here are our best bases because they act as a strong base and are very weakly nucleophilic, so we're not going to get mixtures. So we have NaH, DBN, and DBU, whereas this other box has strong bases that are also strong nucleophiles, so these will result in a mixture. You are not responsible for the structures of DBN or DBU, but do know that if you see these acronyms, these are bases. E2 eliminations, which we saw previously, are bimolecular, kind of like SN2. The bond making and bond breaking are happening at the same time, and that involves this base here. And the base, again, will extract the H next door to the leaving group, or beta 2, the leaving group. So if I had a negative base here, that can grab this hydrogen, and as that is happening, this is also going on. So I'm going to draw the intermediate here, or my transition state. So as that H is getting abstracted, this double bond is also forming in the process. At the same time, the tosyl group is leaving. And then we form this double bond. We also have the base H that forms, and then here we have OTS that gets kicked off. So here we're going to look for our product. We want to pull off the proton next to the chlorine or leaving group, and we also want to form the most substituted alkene. So H next to leaving group, and most substituted alkene is the product. So if I look at my chlorine, my groups that are beta are here, call this HA, and then I have HB. This carbon right here has no hydrogen, so I don't have to worry about that getting removed. So I'll draw both of the products that result. If I take HA, I get that product. And if I take HB, I get this one. A is di-substituted because there are two groups. B is tri-substituted. There are three groups coming off of here, so this is my major product. So you only need to draw the major product, but if it helps to draw the two of them out so that you can see it, you can do that. All right, same thing here, HA. This is also HA, though they're the same. This is HB. Let's just draw out both products again. If I take HA, I get this. And if I take HB, I get this one. So di-substituted versus tri-substituted, this is my major product. In the E1 reaction, this is similar to an SN1 reaction where we have the elimination happening where it's unimolecular. The rate is dependent on the formation of the carbocation again. And the base here is usually a weak nucleophile. So in these reactions, just like in the SN1, our leaving group is going to leave. So I have loss of leaving group. I form a carbocation. This is tertiary, so it's pretty stable. So this so far is looking just like the SN1 reaction. Now instead of having a nucleophile come in, I just have a base that's going to pull off the proton next to the carbocation, so kind of like the E2 reaction, and that will just form the double bond there. E1 reactions don't happen unless it's a tertiary carbocation. We can also do it with benzylic. They often involve weak bases, and we can also use strong acids with heat to remove alcohols. So here's our category of weak base, weak nucleophile. So this might be an indicator that that's the type of reaction that we have going on here. So here, with this one, we use the concentrated acid. The OH is going to form the carbocation via a loss of water. So if I just showed you what steps happen here, I have OH. The acid can protonate that alcohol. And now water is a good leaving group. So I have loss of leaving group. That forms the carbocation. And now we can do the elimination to give us the most substituted alkene, which is that one right there. We do some practice problems here. Ethanol is our weak base, weak nucleophile, and we're going to do an elimination of this tertiary alkyl halide. It's going to result in the most substituted alkene. So we'll get this one. And then for this one here, I'll form a benzylic carbocation, and there's only one proton to eliminate. And we form a double bond right there. So that would be our product of the E1 reaction. Alkyl halides are present in nature. You may not have thought about this, but it was thought originally that chloroform, halogenated compounds, and PCBs were just pollutants. But it turns out that there have been 30 naturally occurring compounds known as of 1970 that had alkyl halides. And that was as of 1970. Now we have over 5,000 organohalides that are known that come from plants, bacteria, and animals. Some animals actually release these as defense mechanisms. Halamon comes from the red algae and has anti-cancer activity. And this large structure here is vancomycin, which is an antibiotic used to treat bacterial infections. And if you're looking for the halogen here, there is one chlorine right there.